welcome to section 5.4. Today we're going to review part 2 of the fundamental theorem and talk about area. It's going to be a fairly short lecture because the majority of it I want you to spend doing problems, and so there's a lot of practice problems for you to do. Make sure you do them. Okay, so the part 1 of the fundamental theorem tells us that differentiation and integration are inverse operations, and so we take out the t and put in an x, and we get f of x. Part 2 is our workhorse. This is the part we use pretty much every day. To evaluate a definite integral, we find an antiderivative, big F, then go straight bar, b and a, and that means evaluate big F at b, and then subtract the value of big F at a. So I'm going to do a couple of problems reviewing part 2 with you. First one, in order to use our integral Bible, the power rule, we need to multiply all of this out. So this is going to be the integral, and I haven't integrated yet, so I have to write the integral sign. 4x squared plus 4x plus 1, just did FOIL in my head, dx, don't forget the dx. Now we're going to integrate. So once we integrate, we drop the integral sign, we drop the dx. So we're at this step right here. So our big F, now I can use the power rule. 4/3 x cubed plus antiderivative of x is 1/2 x squared. A half times 4 is 2, and an antiderivative for 1 is x. Straight bar, -1 and 2. All right, now we put in 2. 2 cubed is 8. 8 times 4 is 32, plus 4 times 2 is 8, plus 2. Then you need parentheses, minus, and when you're dealing with negative signs, it's really important to put that parenthesis there, well, even if you're not dealing with minus signs, because you have to subtract everything that involves f of a. So there might be more than one term, and here there's 3 terms. So I get -1 cubed is -1, so this is -4/3. Then -1 squared is 1, so plus 2 minus 1. Now resist the temptation to simplify this in terms of a single denominator, simplify this in terms of a single denominator, and then subtract. Resist that temptation, because sometimes the fractions will work in your favor. If I look at just the fractional part, I got 32/3, and I'm adding 4/3, right? Because minus a minus, and then this is 10, and this is 1, so 10 take away 1 is 9, plus 9. And here I've got 36/3 plus 9, but 36/3 is 12. So I never even had to find a common denominator. This is 12 plus 9, which is 21. Okay, next one. This is a Bible formula, and hopefully you recognize it as sine inverse. All right, a sine inverse is the one inverse trig function that doesn't have a 1/k out front. So this is just sine inverse of x over 2, because our k is 2. Straight bar, 1 and -3. √3, all right? And so this is going to be sine inverse of 1/2 minus sine inverse of -√3 over 2. Now you have to know your inverse trig functions. So you really do have to memorize these, and if you're wondering where to go to do a review, go up to your section 1415 lecture notes, and I did a review there of the inverse trig functions and the ranges that you have to memorize. So you might want to watch that video again. So let's go back here. So sine inverse of 1/2 is that angle between -π/2 and π/2, whose sine is 1/2. That's π/6. And sine inverse of -√3 over 2 is down here. That's -π/3. So we've got π/6 plus π/3. Get a common denominator, ... You can do that and get π/2. But you have to memorize inverse trig functions: inverse sine, inverse tangent, and inverse cosine. Okay, so let's talk about some area problems. When you want to compute the area bound by 2 curves, you have to integrate top minus bottom. And if the top curve and the bottom curve change halfway through the interval, like they do in this example here, then you're going to need 2 integrals. So find the area of the region between the x-axis and sine x over the interval from -π to π. I've graphed the curve y equals sine x, and I've shaded in the regions we're talking about. So for the first region, so this is Method 1 doesn't use symmetry, method 2 does. The first region goes from negative pi to 0, and the top curve is the x-axis. The x-axis is y equals 0. So our top curve is 0, and our bottom curve is sine x dx. Okay, and then the second region goes from 0 to pi. The top curve is sine x. The bottom curve is 0 dx. So that's the setup if you want to do both integrals. So this would just be negative the integral. This is negative the integral from negative pi to 0 of sine x plus the integral from 0 dx, plus the integral from 0 to pi of sine x dx. If I clean up, take off the 0 and pull that minus out front. Okay, method 2 uses symmetry. If I want to compute this number, whatever it is, it turns out to be 4. I could compute this. You ought to do that. Make sure you can get 2. And I compute this. I'll get 2. Whoops. Oh, there's my plus sign. Let me clean that up. It's sine x dx plus the integral of sine x dx. And this one has a minus out front. So 2 plus 2, you'll get 4. So method 2 says, well, this region here has the same area as this region here. So why not just compute the region, this area, I'll call it A, and multiply by 2. So the second method says this area, I'll just call it area, the total area, is twice the integral from 0 to pi of sine x dx. And when you're doing area problems, if there is symmetry, it really does save work. Instead of having to compute 2 integrals, you can compute 1 and multiply by 2. So let's do that. I'm going to integrate now. The integral of sine is negative cosine. And I've got that 2 there too. Negative 2 cos x. Straight bar, pi, and 0. So that's negative 2. I'm going to pull the constant out. Cosine of pi minus cosine of 0, which is negative 2 times negative 1 minus 1. That's negative 2 times negative 2 is 4. It would not make sense to compute an area problem and get a negative number. Now, asking for the area bound by this curve and the x-axis over this interval is different than just saying, please integrate from negative pi to pi sine x dx. If you do that, you will get 0. Because if I call this, let's call this A1 and this A2, we know that when we integrate just over an interval, any region below the x-axis will count as negative area. And so when I do this integral out, I'll get negative the area of A2 plus the area of A1, and I'll get 0. In fact, let's just see. We get negative cos x between negative pi and pi. So that's negative cosine of pi is negative 1. And I subtract cosine of negative pi, which is also negative 1. Negative 1 plus 1 is 0. So just integrating over a region, you can get over an interval, you can get 0. But if you're computing area, you cannot get 0. And you have to write 2 separate integrals if the top curve switches with the bottom curve. All right, so next one, find the area of the region pictured. So clearly our lower limit on the integral is going to be 0 because the region starts when x is 0. But the question is, what's going to be the upper limit on our integral? So what's that number right there? So our area will be the integral from 0 to question mark. Top curve is 4. Bottom curve is secant squared x dx. So how do we find question mark? Well, we set secant squared x equal to 4, and we solve. So secant is 1 over cosine. So let's just flip both sides of this equation. This is 1 over cosine squared x equals 4 over 1. So I flip both sides, I get cosine squared x equals 1/4. So that means, this implies that cosine x is going to be plus or minus the square root of 1/4, which is a half. Now we're in quadrant 1. We want positive. We want cos x equals 1/2. And so that's going to be x equals pi over 3. So that's our question mark. The area is going to be the integral from 0 to pi over 3 of 4 minus secant squared x dx. So now we'll integrate. So we're going to drop the integral sign. The integral of 4 is 4x. The integral of secant squared, so this comes from the Bible, but you can just think, well, I know that the derivative of tangent is secant squared. So this is going to be tangent x. And then straight bar, 0, pi over 3. So this is 4 pi over 3 minus the tangent of pi over 3. There's pi over 3. Tangent is the slope of the terminal side, which is root 3. And then when I put in 0, I get 0 minus tangent of 0. Tangent of 0 is 0. So that is my final answer, 4 pi over 3 minus root 3. Okay, so for the rest of the time here, I want you to work on some problems. There's one I wanted to do with you, which is B. So let's look at my solution. Well, no, I'll just do it from scratch. In my solution, well, let me just jump down here anyway. In my solution, I have a ... -4. So I want to make sure you can do that ... because it's just basic pre-calculus, but I want to make sure everyone can do that. First of all, this is the integral from 0 to ln of a third of e to the -2x dx. I have to rewrite it like that in order to use my Bible formula. And the Bible formula I'm referring to is the integral of kx dx is 1 over k e to the kx plus c. Now, I won't have the plus c because this is a definite integral, but I will have the 1 over k. So that's -1/2 e to the -2x between 0 and ln of a third. Let's pull out that -1/2. I've got e to the -2 ln of a third minus e to the 0, which is 1. Okay, and then I'll do my scratch paper over here. E to the -2 ln of a third. Before I can cancel the e and the log, I need to bring the -2 up as an exponent. That's e to the ln of a third to the -2. All right, well, if I want to make that a +2, I just flip this fraction. That's e to the ln of 3 squared. Okay, that's 9. E to the ln 9 is 9. So I get -1/2, 9 minus 1. 9 minus 1 is 8. And we get the desired -4 as our answer. So I just want to make sure you can do basic simplification of e and ln, and then of course just very simple stuff like a negative exponent. If you have a over b to the -r, that's the same as b over a to the +r. Okay, and that is the end for me, but you guys have some problems to do.